So I just want to give you some fair warning before we actually dive into this. I'm going to be talking about the geometric meaning and kind of just present it to you, and then we're going to derive the algebraic meaning from that. I'm not actually going to go into the derivation of the geometric meaning of the dot product, and that's actually part of your first homework, is working together in groups to try and figure out how the geometric meaning of the dot product actually came to be. I'm going to be leaving some links down in the description and on the website to some resources that I used back in EMAGS and back in learning physics to help understand the dot product and kind of see how the dot product became a thing. Please do research on your own, read the book, maybe read a couple other books or a couple other websites to try and understand, how the dot product came to be. Our dot product, which hopefully you've seen before, this shouldn't be your first time seeing the dot product. It's defined as the product of the magnitudes of two vectors and the cosine of the smaller angle between them. And the form that it's normally written as is A dot B, which is how it's read, is equal to the magnitude of A times the magnitude of B times the cosine of the smaller angle between them. Pretty obvious. An example that people normally see first is when talking about work calculations in physics. So let's assume that, real quick, that you have a box on the floor and you need to move it, and it's pretty heavy. Let's say it's maybe it's 100 pounds or something, and you're on your own, and you're trying to push it. If you were to push it along the same line as the floor, so the force and the direction, or the length, is in the same direction, there's no angle between them going in the same line, it was very easy to compute the amount of work being done. It was simply the force times the length over which the force was acted. What ended up happening was your teacher, of course, went, now we're going to introduce a little bit less ideal situation in which you actually apply force at an angle. So instead of, getting on the floor and pushing, what if you tied a rope to it and you pulled from standing height? Your force would be at an angle to the resultant direction of the box moving. So to be able to figure out how much force was going in the direction of the floor, or in the direction against friction, you had to introduce this cosine theta term. And it's kind of judging how parallel or how perpendicular the force and the displacement vector were. If you had physics with calculus, then what happened was you said, okay, what if the length and the force can vary with position or time, depending on, what you're computing. What ended up happening was you needed to then break up your calculation into an integral. So what you ended up doing was multiplying the force over these differential lengths. Hey, there's that key word again, differential. So you took your force vector and multiplied it by the differential length vector, and you were looking for a scalar. You were looking for the overall work. That's normally where you first see the dot product. Unfortunately, one of the biggest problems with this geometric meaning, even though it's pretty simple, is actually having to know the angle between the two vectors. Now, in 2 dimensions on pen and paper or on a computer, it may not be hard to find the angle between them. You can measure them pretty accurately. But when you get down into 3 space and 3 dimensions, it's a little bit harder. If you really wanted to see it, take your arms, hold them straight out in 2 directions, and try to estimate the angle between them. It's a little hard. So because of this, and we can't really find a good way to measure the 3-dimensional angles, and you're not going to be expected to do that on a test in 2 hours and 30 minutes, what we need to do is actually find another meaning of the dot product, or another definition. So to be able to derive this second definition, we're going to, again, consider 2 vectors, A and B, but we're going to represent them in component form. So using the a hat x, a hat y, and a hat z vectors, and using it as a sum of those 3 components. The nice thing about the dot product is, since it's basically multiplication, it obeys the distributive law, which means that we can actually break up A dot B into a sum of 9 different terms. And you may be thinking, well, what the hell? How is that easier? One of the first things you can do is actually rewrite the equation so that all the components, like AX, BX, are in one set of parentheses, and then the dot product between the unit vectors are in another set. This way you can kind of just focus on where you actually need to apply the dot product. So as you can see, kind of looks a little bit nicer, but it's still a huge equation. Once you start actually looking at the relationships between the unit vectors, it becomes pretty simple. So we know that these unit vectors for rectangular, a hat x, a hat y, and a hat z, are orthogonal with each other. So this means that as long as it's not a pair of vectors that's a hat x and say a hat x, as long as they're non-similar vectors, unit vectors, they're going to have an angle of 90 degrees. And once again, that's because of the orthogonality. So because they're at 90 degrees, if we set theta equal to 90 degrees, and we go back to the geometric definition, there's a cosine term. Cosine of 90 degrees is 0. That's great news. That simplifies a lot of these terms down. What about the pairings that are similar, like our first term here, ax, bx, a hat x times, are dotted with a hat x? The angle between a hat x and a hat x is 0, right? So your theta becomes 0, cosine of 0 becomes 1. So one of the ways you can kind of think about this is when you do this distribution, the only terms that survive distribution are those with similar unit vectors. And because of this, our equation reduces to a dotted with b is equal to the sum of the similar components multiplied together. This is the algebraic definition of the dot product. This is the one that a lot of people like to use first. And one of the cool things is, since these are both definitions of the same value, some same scalar, you can actually use the two definitions to find the angle or find a specific, component if it's missing. So in problems where it's asking you to find the angle between two vectors, and they give you the definition of two vectors, say 1a hat x plus 2a hat y plus 3a hat z, you can actually find the angle between them pretty simply. One of the main things, though, that you need to realize is that the dot product gives you a scalar. I mean, go back to the algebraic definition. It's a number times a number plus a number times a number plus a number times a number. It's a scalar. One of the more powerful uses of the dot product, other than finding the angle, is actually finding how much of one vector lies in a direction. So once again, go back to the force example with a box. So you're pulling on it with a string, and let's say you're 6 foot tall, and pulling on that string, you can actually start doing comparisons to say, okay, what if I hold it at 4 feet? What if I hold it at 5 feet? And see which one's going to give you more force in a given direction, so sliding against the floor. To be able to do this computationally, the first thing you have to do is perform the dot product. So in the case that the book uses, there's a b vector, let's call this our force vector going up to our, say, chest, and the a hat vector. The reason that they use a hat is because it's a unit vector, and we're just going to say this is the direction in which we need to pull the box. So when you do b dotted with a, you're going to get this length, which if you look at this, basically what forms a triangle, the bottom leg is going to be b dotted with a. There's your magnitude. But what if you wanted a direction? Because what if you need to break up your calculations into different parts? Or if there's varying paths? What happens is that you then multiply your component that you just figured out, b dot a, with the vector in question. It's actually pretty easy. So you just take b dotted with a and multiply it by the a hat vector again.